Hi, folks. Welcome back. I hope you're all doing well. I think that the economics of programming and of application architectures in general is something that is woefully inadequately covered in most computer science curricula. So I was really excited to see this paper by Jim Gray, which talks about exactly that. Jim Gray was a Turing Award recipient for his contributions to databases and transaction processing, and he wrote this technical report back in 2003. So this predates the iPhone, it predates what we would now call the cloud, but it still makes some very fundamental observations about the cost structures of different application architectures. Now, to start with, he makes the observation that for consumers, in some sense, computing is free because large services like Google and Hotmail are free to the consumer. Of course, it's not actually free, but it's paid for by advertising. We also see that these large operators, when they have infrastructure at such a large scale, can achieve really good economies of scale and have a relative overhead as a fraction of their size that's quite low. But those same economies of scale often do not carry over to smaller operators. And that differential was one of the key motivators for companies moving to the cloud. That brings us to the central question being tackled in this paper, which is, what are the economic implications of structuring your applications in different ways? At a very basic level, every application is going to need some networking, some compute, some storage, which here the author breaks down into just raw storage and database accesses. And the important thing is the ratios among the costs of these basic resources. Looking at typical costs at the time this paper was written, the author found that for approximately $1, you could get all these different computational resources. So for $1, you could get 1 gigabyte sent over the network, or 8 hours of CPU time, or 1 gigabyte of disk space. And from these ratios, you can tell that if you want to make a mobile application in the most ideal conditions, it would consume very little network bandwidth, but have a lot of computational demand on the back end. Now, if you update these numbers to the present day, of course, everything is a lot cheaper. So if you just look at some AWS prices, for about $1, you can now get nearly 40 hours of compute time and about 11 gigabytes of network bandwidth. So everything is a lot cheaper, but the ratio has changed. So here we see that the CPU to network ratio is about 8, but with current prices, the CPU to network ratio is about 3.5. So essentially, we're seeing that networking improved faster than compute over the last decade or so. Now, of course, we see that most mobile applications cannot be stateless and are not so compute intensive. If you look at most applications like mail or web serving, they do not fit this ideal profile. They're very chatty over the network and they store a lot of state on the server. So this brings us back to some very basic tenets for constructing distributed applications. The first of which is to do your computation close to where your data lives. You don't want to be transferring a lot of data over the network. You want to push the computation as close to the data as possible. And of course, most real applications will need to read data from multiple sources. And if you want to push as much of that processing close to the data, what that essentially means is that each data source should have its own API which does the processing close to the data. As the author acknowledges here, this whole analysis really turns on the relative cost of compute versus networking. If networking prices drop faster than Moore's law, then these constraints don't hold. So that was a paper that took a quick look at the cost implications of various networked application architectures. I hope you enjoyed that, and I will see you next time. Thank you very much.